Thanks for having me in this session. And I would like to discuss some of the ongoing work in our lab, where we try to basically study how to characterize functional connectivity using resting state, using potentially alternative metrics that might be useful in population-based discrimination. So to begin with, a little bit of a background. So our lab is interested in looking at brain reorganization after an event of stroke. And so typically we see patients coming in with stroke that have clinical deficits in one or more of their brain functions. But recently we've also seen that patients also exhibit what is known as subclinical deficits, which are much subtle and much more moderate in comparison to clinical deficits and are harder to identify or diagnose. And so in order to kind of facilitate rehabilitation and recovery, it's important that we identify these in a timely manner. So the standard way of identifying subclinical deficits currently is using neuropsychological testing, which is basically a series of tasks that we make the patients do, which right after an event of stroke can be a little time and task intensive for the patients. And so alternatively, we proposed using an neuroimaging method to basically try to do the same thing, basically use resting state fMRI, which might both be time efficient as well as task-free for the patients. And so overall, we've started focusing on subclinical language deficit in particular. So we have three groups here. LD plus is the stroke group with subclinical language deficit. LD minus is the stroke group without subclinical language deficit. And HC is a control healthy group. So the goal was to distinguish between these three groups on the basis of verbal fluency, that the scores that we get from the neuropsychological testing. And so we did this using resting state fMRI, as I said, and we collected the data on 3T-GE scanners. We pre-processed the data using standard methods in the field, and then we extract the signal of interest, which is the bold signal. And based on the bold signal, we then define the functional connectivity, which is basically measuring statistical dependence between bold signals of anatomically distinct brain areas. And it's common practice to quantify functional connectivity using Pearson's correlation. However, let's look at this example. These blue and red signals represent bold signals from two distinct brain areas within the language network in a healthy participant. Visually, they don't look very correlated to each other, and the same is also reflected by Pearson's correlation on a scale of 0 to 1. However, when we look at similarity in the frequency domain, the similarity is relatively higher. When we look at the similarity in wavelet domain, again, the similarity is relatively higher. So that kind of led us to thinking is if Pearson correlation alone can completely quantify functional connectivity, at least in cases where the groups are very similar, like the two stroke groups, where we are trying to identify differences. So to investigate this, we basically looked at a couple of different alternative metrics to define functional connectivity. And then the list is not exhaustive by any means. We just tried to incorporate some measures from the time domain, from the frequency domain, from the wavelet domain, some measures that use or measure similarity linearly and others non-linearly. Some measure similarities while others measure dissimilarities. So quickly just going over what each of these different metrics do. Cross-correlation is very similar to correlation, except if red and blue in the top panel are two signals that we have, we account for any possible shift or delay or lag there might be between the two signals. We align them by accounting for that delay, and then we measure this correlation between the two signals. Incoherence basically measures the frequency domain similarity between two bold signals. So here the idea is to look at every frequency component that exists in the two time courses, and then to measure the similarity across all those different frequency components. The frequency components are on the x-axis and the similarity is on the y-axis. In mutual information, we try to model the two signals x and y as random variables. And we account for the mutual information, which is the shared common information denoted by I, while removing any kind of uncertainty that might be caused in one signal due to the other, represented by H. Dynamic time warping is a nonlinear similarity measure. So in the top panel, we see the red and the blue signals. And the idea here is to nonlinearly stretch and squish, say, one signal to kind of match the other one, and then measure the similarity between them. So in the bottom panel, the blue signal has basically been stretched to match the red one as closely as possible. In Euclidean distance is just a dissimilarity measure. It basically takes into account the squared differences of corresponding points throughout the two signals. City block distance is again very similar to Euclidean, but it doesn't take into account square differences. It just looks at simple differences across the different time points. And finally, we have wavelet coherence, which basically is a wavelet domain similarity between two time courses or Bolt signals. So here we account for both time and frequency information simultaneously. And the idea here is, even though overall two signals might look very dissimilar, which is represented by the blue coloring throughout the time frequency plane, there might be hot spots denoted by the bright yellow regions, so points in time and frequency where the two signals can share higher similarity. So with these different metrics, we tried to then do the classification between our groups of interest in the context of machine learning. And so to do that, what we do on an individual level is basically define a network of interest. So in this case, it was the language network, because we were trying to characterize the subclinical language deficit. And then we tried to compute the functional connectivity matrix based on the bold signals that we extract from each of the regions in the language network. So we compute a functional connectivity matrix for each of the metrics that I just described. And because this is a symmetric matrix, we just extract either the lower half or the upper half of the matrix and throw out all the duplicates. And we repeat this for all the subjects. Once we have aggregated this data for each of the groups of our interest, again, LD plus was stroke group with subclinical language deficit, LD minus was stroke group without subclinical language deficit, and HC was the healthy control group. Once we have gathered all the features for each of those groups, we perform a feature selection method to reduce the number of dimensions of features that we might have. And then we feed those selected features to a standard machine learning support vector machine classifier. And we validate the result or the performance of the classifier using a leave one out approach. So based on this pipeline, we basically try to validate our results in a couple of different data sets. So to begin with, the main data set that we wanted to test was trying to test not only differences between healthy and stroke people, but also variations or differences within the stroke group. So we recruited 60 right-handed participants for this particular analysis. All the groups were matched in terms of age, gender, and education. The only thing that they didn't match was in terms of their verbal fluency scores. And then basically what we try to do is we look at the language network and look at the classification performance. So as we see, we have in the second and third row, we have distinction between the stroke and healthy groups, which is, again, relatively easier to distinguish. But the more difficult one was the first one here, trying to distinguish between the two stroke groups. And as we see, Pearson's correlation does not necessarily perform the best when compared with all the other metrics. Some of the metrics that stood out were coherence, dynamic time warping, and wavelet coherence. So we also tested this in healthy participants. So we looked at age differences. We recruited 50 right-handed participants, with half of them being old and half of them being younger. And we looked at not only language network, but also other networks in the brain. And similarly, there we see that Pearson's correlation does not necessarily perform the best in comparison to all the other metrics. But interestingly, when we combine information across all these different metrics, the combined metric always performs better, or at least comparably, when we compare to the individual metrics. We also similarly validated this with gender-based differences. We looked at 48 right-handed people, half of them male, half of them female. Again, Pearson's correlation does not necessarily perform best, but the combined metric does outperform all the results, all the other metrics. And so basically what I wanted to emphasize here was that Pearson's correlation might not always be the most optimal metric to quantify functional connectivity. And instead of trying to find one superior metric, what might be more useful would be to combine information from different domains that might help us quantify a more functional connectivity more comprehensively. And this might especially be useful in identifying differences between similar groups like the two-stroke groups I just showed. And so because it uses information from time, frequency, and wavelet domains, similarity and dissimilarity measures, we might be able to understand the dependence among bold signals a little better by combining information from different domains. So I would like to thank my lab group at University of Wisconsin-Madison and the funding resources, and thank you for listening.